Traditional institutional finance relies on reputation-based systems. Because this trust is highly subjective, counterparties maintain isolated private databases. Reconciling these records requires constant manual intervention to correct discrepancies when two systems don't align. Decentralized systems attempt to bypass this with distributed consensus. However, standard smart contracts execute logic in isolation. They lack a native link to the legal, jurisdictional, and economic reality of the assets represented. Both models share a common structural vulnerability. Whether the system depends on a bank's reputation or a blockchain's consensus, institutional trust is assumed. Neither paradigm mathematically constructs that trust from verifiable evidence. This failure is defined here as the trust gap. It is the point where assumed trust breaks down, leading to the manual reconciliation and operational overhead that plague modern finance. A fiduciary system that relies on these assumed trust models is poorly suited for digital assets. Without mathematically proving every state transition, the system remains prone to error and fraud. To address this, B Family Operations engineered the Institutional Digital Asset Operating System, or IDAOS. It is a deterministic computational model designed to mathematically prove the state of an asset. At its core, the system functions as a trust compiler. In software engineering, a compiler transforms high-level source code into machine instructions by passing it through an intermediate representation, a standardized middle step that ensures the final output exactly matches the programmer's intent. IDAOS applies this logic to fiduciary management. It takes raw evidence and legal rights and compiles them into a canonical digital state that exists independently of the underlying technology. Structurally, the token serves as a regulated transfer interface. It does not create ownership or value. It acts as a pointer to the specific rights established and compiled within that digital state. Treating fiduciary management as a strict compilation pipeline ensures that every digital representation is a verifiable reflection of its legal and economic reality. The IDAOS architecture is organized into 4 decoupled layers. At the foundation is the data plane. This layer houses the digital twin. In domain-driven design, this is the aggregate root, the living, stateful object that serves as the canonical source of truth for the asset. Traditional databases store current balances by overwriting previous entries. If a record is changed directly, the history of that transaction is lost, making it difficult to audit the system without relying on external logs. IDAOS solves this with event sourcing. The digital twin is not a single, mutable file. It is a linear, append-only ledger of cryptographic event blocks. The current state of an asset is not a static number in a cell. It is a projection, calculated by replaying the immutable log of events from the moment the asset was created. Because this ledger is append-only, existing data cannot be altered or hidden. Every financial event is permanently locked in sequence. This structure ensures that every current balance is mathematically traceable to an immutable historical fact, eliminating the risk of silent accounting errors. Sitting directly above the data plane is the trust compiler layer. It acts as the system's execution engine and gatekeeper. This layer enforces command query responsibility segregation, or CQRS. CQRS separates intent from fact. A command is an untrusted intent. An event is a verified fact accepted into the ledger. Every command passes through the policy engine, a directed acyclic graph evaluating requests against governance and compliance mandates. The engine functions as a finite state machine. If a command violates a rule, like attempting to distribute yield before the record date, the policy graph fails and the request is rejected. Only commands that satisfy every node in the policy graph are compiled into permanent events and written to the data plane. By separating intent from the ledger through a policy graph, the architecture prevents malicious actions or operational mistakes from corrupting the canonical state. Many decentralized systems suffer from the Oracle problem, where they trust external APIs to automatically trigger state changes inside a smart contract. If a system makes a live API call during an evaluation, it loses its determinism. Replaying that transaction later for an audit could yield a different result, making the record unreliable. IDAOS maintains a strict reality boundary using a hexagonal architecture of ports and adapters. These adapters normalize messy external data into standardized, cryptographically signed evidence packages. These passive packages do not execute logic. They are deposited into a static reality cache. Every source is assigned a trust level from T0 to T4, establishing exactly how much consensus is required before that evidence is considered admissible for a decision. When the policy engine evaluates a command, it queries this static cache for the verified evidence valid at that specific timestamp. It never makes a live API call. By demoting active oracles to passive evidence providers, the system ensures that its functions remain deterministic and fully insulated from external data churn. Time often poses a threat to deterministic systems. Software typically relies on automated cron jobs to trigger actions, which can be unpredictable and difficult to replay. IDAOS governs this with Axiom 6. Time creates eligibility, not state. Here, time is another form of evidence. The temporal compiler converts a clock feed into a time evidence package in the reality cache. Passive temporal watchers monitor this. If a deadline passes, the watcher prompts the policy engine to evaluate delinquency without changing state. This logic allows for the final two layers, the governance control plane and the experience layer. The user interface, the experience layer, is strictly a client. It is entirely stripped of database edit privileges. The dashboard functions as a cockpit for human review. It assembles evidence, active policy rules, and the asset's current state into a pull request for the operator. Human authorities review these validated requests and provide the cryptographic multi-signatures required to authorize the final command. Isolating human actors to this unprivileged experience layer removes the primary vector for enterprise fraud and operational error. Trust is built into the architecture, not the individuals operating it. This completed four-plane architecture provides three core values: institutional certainty, technology neutrality, and audit-proof compliance. Imagine a regulator requires absolute proof of a fund's state and its ownership records from exactly 3 years ago. The verifier audit.go script provides a way to execute these historical audits. It performs a complete recalculation of the ledger to prove that the current state is the only mathematically possible outcome. Because the system is self-contained and deterministic, it can rewind the event ledger to any exact millisecond in the past without calling any external APIs. The historical state is recalculated using only the cached evidence and the specific version of the policy graph that was active at that moment in time. Legacy finance requires months of manual reconciliation and sampling to produce a report like this. IDAOS produces a cryptographically verified proof in seconds. By building on these 6 axioms, IDAOS establishes a system where every state transition is a calculation derived from evidence. It provides the technical infrastructure to maintain a canonical record that is mathematically reproducible and ready for audit at any moment.